Okay, good morning. Let's quickly finish the last example about transient analysis of signal down the transmission line. Last subject, we talk about when the load is not resistive, but reactive. Okay, reactive component include inductors, capacitors, or the combination of two. Right. So we have two examples. The first example, we are talking about a transmission line, and at the end we have inductor, right? And because inductor, we know by definition of inductor, the voltage across inductor and then current goes through the inductor is according to this is definition, right? And then we said, you see, from the definition, we can see the voltage proportional to the derivative of current versus time. What that means is the current must be continuous across the time. When the time t, the current is time t minus must be the current t plus, right? Okay, so this is the reason we draw these conclusions from definition of the current the current derivativity when we define inductance. So from this relation, okay, from this relation, we can find a voltage. We can find the voltage. We can find the voltage. This is the current. The current continuity condition. From this current continuity condition, we can find the initial condition for voltage. Okay, so this is one very important thing is because we are solving initial condition problem, we must know what is the initial condition is. Okay, and another thing is that because we are dealing with one inductor, one resistor. Okay, so this is the first order transient problems. So we have to solve. We need to solve we need to solve the total voltage across inductor must be equal to the incident voltage. This is the incident plus reflected voltage, right? So that from here we can build up the first order differential equations, okay? And also, this is also when we look at this inductance on other side, this is one resistance, right? Then we can find the time constant tau, right? So the from this we know the reflection from the differential equation we have, and also time constant, we know that, and also we know the steady state. This is a steady state. Okay, steady state, then we can construct what this solution is, right? If you're not sure why this is true, then you can substitute this into our differential equation, okay? to say if this is satisfied. Okay, if this is satisfied, so the solution is correct, right? So the only thing we haven't decided is this constant A. Okay, we determine this constant A by initial condition. Okay, by initial condition. So initial condition determines this constant A, right? So we can determine this constant A. Then we substitute constant A into the solution. We can find reflect voltage, and also once we find the reflect voltage, and because this voltage is reflecting travel in minus z direction, so the relation with the current, okay, don't forget we have a minus sign and divide by characteristic impedance. Then we find the solution. Okay, now that is a quick review of the first example we have deliberated last week. Okay, now let's finish the second example. Okay, by the way, in the final exam, we have one question regarding this transient analysis. Okay, so let's look at second example. This is a very different type. Okay, but I gave some clue. Okay, I give some clue. So we like to find the voltage. Okay, we like to find the voltage and the current at both at the load and at the source. Okay, but we have a capacitance located in the middle of the transmission line. But because the material is different on the both sides, okay, so we have on left-hand side, the characteristic impedance is 50 ohms, which match to the source impedance. So that means the wave hit on the source and the reflection 0 because matched, okay? And on the load side, the load impedance is 50, characteristic impedance of the connecting line is 50, so also not reflection coefficient, okay? And we gave a hint, okay? First, okay, we try to find the voltage and the current at input. Let's say we find the voltage and current at z equal to 0 location. Okay, let's find this voltage, okay, and also this current. Okay, it's z equal to 0, right? It's z equal to 0. And also that suggests us considering the initial and the final behavior. Final behavior is what? Final behavior is a steady state solution. Okay, the steady state solution, look at this, okay? We have initial condition. The initial condition is we have no charge. Okay, where is that? Okay. The initially uncharged. Okay, read this problem. Initially no charge. Initially no charge means the initial voltage across capacitor 0. Okay, because there's no charge, there's no electrical field. Okay, so this is first thing, right? Second suggestion is let's use the initial and the final behavior of the capacitor. Let's determine this voltage. Okay, let's determine this voltage. Now, let's recall what the definition of capacitance is. The definition of capacitance is, if we have a voltage, we have a current, okay? So the current goes through the capacitance is proportional to the voltage across capacitance directivity with respect to time. And then the proportionality constant we call capacitance, okay? Okay, this is called capacitance, right? Now, this is a second clause, okay? This is second clause. And the third clause is, I just mentioned, voltage across capacitor cannot change instantaneously. So you cannot arbitrarily change. So that means if this is a voltage, okay, if this is a time, okay, if this is a voltage, you cannot change abruptly, okay? This is not correct, okay? It never happened, okay? Because of this, okay? And the fourth clause, okay? The fourth clause is, if we have a capacitance, okay, then when you're looking toward both sides, what you can see is this side is a 150 ohm resistance. This is instant voltage or current through the capacitance, can see, right? And this is 50 ohm. Okay, so this is the first order circuit problem. Right? This is first order circuit problem. The time constant tau, okay, that should be equal to C times R. Okay, so I don't review why this is C times R. You go back to check your basic circuit theory. Okay, so that had a very detailed analysis. Okay, so this is time constant. Now let's construct. Let's see how we construct the solution. Okay, first, let's find initial voltage, right? Let's find initial voltage. Initial voltage is once the switch is on. Once the switch is on, okay, the battery is connected, and what you can say is only 50 ohm, right? So this circuit become 50 ohm. Sorry, 50 ohm, right? So the initial voltage is this plus. Okay, this is the initial voltage. What that equal? This is a 20 volt. So this is voltage divider, right? So this must be 20 volt divided by 50 plus 50, right? Times 50. Okay, so this is 10 volt. So that means once it's turned on, okay, turned on, then the initial voltage is 10 volt. So that is one time 10 T0 turned on. So this is a okay. And how long it takes? So this 10 volt voltage go here, and then at the beginning, because initial voltage across capacitance is 0, right? So therefore, when it hit it on, the voltage across capacitance should be continuous. So that's still 0, right? Once it is 0, then what it says is as if this is connected, okay? Because no voltage drop, right? Then what is you say is 50 ohm, the 150 ohm, this is 50 ohm, then tell me what is the voltage reflection coefficient. It's 150 minus 50, 150 plus 50, right? Okay, this is a 1/12. This is voltage reflection coefficient. So that means we have 10 volt hit on this boundary, and we have a reflection. What this reflection is 100 volt times 1/2, right? So that means this is 5 volt. Okay, this is 5 volt. So the 5 volt travel another t times. So once this reach back, okay, this is 10, this is 5. At what time? It is 2t time, right? At 2t time. So at the source side, okay, now the voltage at this time, 2t time, equal to 10 plus 5, okay? So that means that jump to here, okay? The voltage across here can be jumped, okay? Only I said the voltage across capacitance cannot be jumped, cannot jump, right? Because voltage across capacitance should be continuous, okay? But the voltage across the source, okay, here, this voltage can jump, okay? So the jump from 10 to 50, okay? So this is our initial time. Initial time, 1 t equal to 2, okay? 2 what? 2t, okay? 2t, right? So we treat this as our initial time, okay? Initial condition. So we said the first close, I remove the first close. We suggest from initial time and the final behavior to determine this voltage at the source side. Okay. Now we need to predict what? We need to predict what is this, and then also at infinity. At infinity, let's say, do we know what is voltage at infinity? You see, at infinity, once the switch is on, you have some transient voltage. But after a long time, okay, this transient die away. And then the current goes through the capacitor, doesn't change with time anymore. Or the voltage across capacitance doesn't change with time. So that means this approach to 0 at t equal to infinity, right? Okay. The current goes through the capacitor after transient oscillating, okay? Die out, so approach to 0. So when current approaches 0, so this part become just open circuit, right? So the current 0, okay? Current 0, okay? Tell me what is voltage across capacitance. So because no current, voltage, the voltage goes through all this part, voltage drop 0. Voltage drop from here also 0, right? Because no current value can have a voltage drop, right? Okay, so it ends up the voltage everywhere between these two equal to 20, right? 20 volt. So that means That means this is 20 volts, and then this, the asymptote of this curve is 20 volts. Okay, now we have all the information we need to determine this part. Okay, why is this? You see, because we know this voltage, the voltage is the source. This is voltage is source. This is voltage. Must, you see, steady state is a V0. Okay, because this is first order transient problem. Then we have arbitrary constant we need to determine. Okay, then we can write the solution in exponential form, right? Because this is first order problems, right? And then we know time constant tau. Okay, then our initial time by now is 2t, right? So or 2 nanoseconds. Okay, now we use t minus this initial time, right? Okay, so this is initial time. This is initial time. So that means when t equal to t0, okay, that is our initial time. Okay, that is our initial time. We already know the voltage equal to 50 volt, right? This is 50 volt. Okay, this is 50 volt. So this is our T0, right? This is our T0. From here, we can determine, we substitute this to the initial time into this. Okay, that is our initial condition. This is the initial condition, 50 ohm. Oh, sorry, 50 volt. Then we know A. We know what A is. Okay, we know what A is. So we substitute A. Okay, substitute A because V0 is 20. So we know A is -5. So therefore, we know the overall voltage. Overall voltage at the source terminal. Okay, at the source terminal. So once we know the voltage, can we know the current? Yes, of course we can. You see, because what we have is this is 50 ohm, this is 20 volt. Okay. Now this is a voltage. This is our define. Then if this is current, what do we have? KVL. So that means you see all our subject is all interrelated. Why we emphasize those basic circuit, you see, basic theory, right? Such as circuit theory, right? But you see, the circuit theory we use all the time, right? So if we use KVL, KVL is always correct if the length of the connecting line is negligible, right? So we use KVL. What that means is minus 20 volt because this direction, right? Plus 50 times current, okay? Plus V equal to 0, right? Then can we find I? Okay, so I is 20 minus V divided by 50. Okay, this is this, right? Because we already know V, we know current, right? Then one checking point is, so not checkpoint. So if you are interested in what happened when t equal to 4 nanoseconds, so you just substitute the t into this, right? then you can get the value. So that is this point. All right, so we finished chapter 6. Okay, that is a transmission line for digital circuit. Okay, we have many more subjects to relate to this, but we don't have time to discuss. But however, you see, if you understand this very basic concept, it's not difficult for us to understand a more advanced subject. Even if you are interested in, you can go back, you can go to textbook, you can read, you can learn by yourself. Now, let's move to next chapter, the transmission line for communication. Okay. When we deal with digital circuit, we pay attention to time domain analysis. Okay. But when we do the transmission line for communications, we are interested in the response in frequency domain. Okay, because we always talk about broadband, or we talk about microwave frequency, radio frequency. We all talk about in different frequency band, right? So if we understand the response at a certain frequency, at certain frequencies, then we can very well describe the property of the system. Okay, when we go back to review what we have learned, right? In basic, in transmission line for digital circuit, when we derive the equations, okay, when we derive the time domain equation for voltage and current, we didn't consider loss, okay, because in that time, the loss is not a major concern. But in communication system, the loss will be a major concern. Okay, let's start from simple circuit first. What we learned is giving a transmission line can be represented by many sections of, okay, of this. This I call a unit circuit. Okay, that is a series inductance, shunt capacitance, shunt to ground. Okay, this is ground. Okay, so this is ground. And then the L and the C is inductance and capacitance per unit length. Okay, per unit length. So that's why if you're talking about a very short transmission line, okay, with the length dz, so the total inductance will be, or total capacitance will be unit capacitance times the length, right? Because it per unit length, right? So we must multiply by a length. Okay. We also justify the characteristic impedance is square root of L over C, and the phase velocity is 1 over square root of L, right? So this is similar to in plane wave. We also have in plane wave, we have a characteristic impedance that is mu divided by epsilon, right? And also in that subject, okay, we have this. So therefore, inductance correspond to mu, okay, capacitance correspond to epsilon, right? And we also know the voltage and current, we have propagating, one way propagating in that direction, then we have another way propagating in minus that direction. Okay, so this stands for wave, right? Okay. So this is a wave in positive that direction. Same as current. Remember, for current, when they propagating in minus z direction, we must have this, okay, minus sign, okay, minus sign. So if you talk about traveling wave, okay, the current voltage and the traveling wave voltage and traveling wave current follow Ohm's law, right? Follow Ohm's law. Then, if we are interested in frequency domain, what that means, we can use phasor again, okay? We use phasor again, okay? When we talk about phasor, then we talk about the instantaneous. Okay, so this is a pair. So this is time domain. This is frequency domain. Okay, this is frequency domain. So the time domain instantaneous things for giving frequency omega, we can write in terms of cosine, right? So then if you match the okay, and again voltage current related to characteristic impedance. So I have repeat this truth 100 times, right? And then people has a saying is if you repeat a lie 100 times, the lie become truth, right? So I have repeat truth 100 times, so there must be truth the square, right? Okay. Now let's extend the circuit model, okay, further, including a loss, okay. Previously, for lossless case, we have series inductance and shunt capacitance. That's it. Okay. Now we said, okay, this is not enough for communications because conductor has a loss. Okay, because conductor has a loss. Okay, and the substrate. Okay, say if you have coaxial cable, say. Okay, conductor has a loss because you have a conductivity. Okay, then you have R. Okay, the substrate, you have a loss tangent. Okay, or your permittivity has a real part and imaginary part. Okay, so you also have a loss. Okay, that means this also could be a lossy, right? And then this is our ground, right? You also have the loss is a lossy. So how to reflect this? Reflect by a conductor. Okay, so you have basically resistance, right? Okay, so this is a resistive component, not a reactive component. Reactive components are lossless, like pure L, pure C is lossless. Okay, so that right now we can see capacitance is lossy, inductance is lossy, right? Okay, now we understand this is all circuit parameter per unit length. Okay, I emphasize this is all per unit length. Okay, per unit length. Okay, with this circuit per unit length. Okay. Oh, sorry. This is. very short length, okay, very short length. Then let's apply KVL and KCL. KVL and KCL, okay? So how to apply the KVL, KCL? If you apply KVL, so voltage here equal to this voltage drop over resistance, voltage drop you see, because this voltage is our reference direction, so the other voltage will be negative direction, okay? So this is our definition of voltage, So, right, so we have a voltage across inductance, okay? And then the voltage here is after a very short length, okay? Very short length, because from here to here, we have a certain length. Don't forget, we have a certain length, okay? This physical length create a difference in voltage, okay? These two voltage is different. The current is also different, okay? So therefore, the first equation, we generate a differential equation, okay? The differential equation, what I use, okay? The V I take limit okay, I use a partial directivity because this is multiple variables. Okay, I use this. This is also a function of time, right? Function of time. Okay, you see, because this is too short, I can say it happened. Voltage difference, current difference happen is almost in the same time. It's too short, because this is electromagnetic wave travel is too fast. Okay, so we have one equation. Now let's look at the other KCL. Okay, the KCL, we apply KCL is the voltage go in, which is this, go into this node equal to the voltage go out, right? The voltage goes this. Oh, okay. You can log in, right? How long do you need? Okay. So I give you 10 minutes right now?
Next tomorrow.
Tomorrow?
Yes.
Let's do it tomorrow. Okay, thank you. Okay, we have another current, So we have a three current, okay? The first current goes through inductance. This is the first one. The second inductance go to, second current go to the capacitance, the second one. Okay, so this is third current. This is third current. Okay, again, we can generate another differential equation. Okay, another differential equation. Now, from these two differential equations, okay, from these two differential equations, if we only consider time harmonic waves, so this voltage I can write in this, right? So this is not new anymore, right? So this is instantaneous. Okay. This is phasor. Okay, right? If you convert phasor into instantaneous, easy, right? You multiply this and take a real part, same as current. Okay. The advantage of having this is if you take the partial v, which is a function of time, this is simply this. Okay, simply this. Right. So the time derivativity is replaced by j omega. Okay, so all the other things will remain the same, but we eliminate one variable. Okay. Okay, now we have another time instant, right? Having had this, okay, we take the first equation on both sides, have another derivative with another time derivative with z. Okay, then we have minus so actually right now it's not a partial anymore. So this should be okay. That's okay. All right. So right, then I substitute this into this. Okay. So the partial I partial z equal to v, right? This is this equation, right? So you substitute this into this. You substitute this into this. So easily we can find this equation. Okay. So this become single variables, but the second order differential equation. Right. So very easily we can find, you see, because after you substituting this into this, we have okay, I define this as gamma square. All right. So this is the equation for voltage. Similarly, you can find the equation for current. Okay, equation for current. The lucky thing is this is a single variable differential equation. So we call this equal second order ordinary differential equation. The solution for second order ordinary differential equation, we have two solutions. Okay, one corresponds to the wave propagating in that direction, and another is minus that direction. And then we know the solution for is exponential function. I'm sure this is we have learned this in engineering mathematics, so I don't repeat this, right? Similarly, we have a current. Okay, similarly we have a current. Then it's very straightforward. We can, okay, we have these two equations. Okay, let me copy one. Okay, this V and I is arbitrary V and I, okay? Is the total voltage, okay, total voltage of V and I. The special case of the V and I, if V equal to V plus, that means non-reflection, okay? Then I equal to I plus, right? You substitute this, then you substitute this, substitute V equal to you substitute this and the current equal to into this. You can find this. Okay, you can find it. Okay, I don't repeat. So this is too trivial. Then, in other way around, okay, if V equal to V minus, then I equal to I minus, then that means V equal to minus plus gamma z, okay? I equal to I0 minus plus gamma z. You can find you can find what the equal to minus R plus J omega L over gamma. Okay, so this is not given by me. Okay, this is given by Maxwell equations. Okay, it's a solution of Maxwell equation or the wave equation. Again, you can say we have this minus sign. Okay, for wave propagating in minus z direction. Okay, you can easily justify this. Okay, if you don't remember this, okay, if you don't remember this, you have to remember this. Okay, for this equation, you have this solution. All right, then you have to remember we have these two differential equations. If you still don't remember these two differential equations, okay, you remember this two, okay, then you know the relation between phase and the instantaneous, right? If you still couldn't remember, okay, if you still couldn't remember, but you have to remember KVL and KCL, right? And also this circuit model. This is the basic things. This is the basic things I required. Only this slide, okay? If you have this slide, okay, you have everything, okay? You have everything. The transmission line story starts from here, okay? That takes you less than 5 minutes. You can derive all these relations, okay? Up to this slide, up to this page. So this is a general transmission line description for communication in frequency domain analysis. Let me say a few more words about the final exam, okay? The questions is already submitted to university, and we have 4 big questions, okay? And then that include almost, you see, we have we emphasize on transmission line, and then with the transmission line for digital circuit, transmission line for communications, and also the material we are going to discuss in next 1.5 weeks. And again, I emphasize, we have to do all assignment. And I can guarantee you, if you know how to do assignment, every problem by yourself, you should be guarantee you can at least 75%. Okay. If you don't do it, if you fail, don't blame me, right? I already tell you the most I can tell, right? The most I can tell. And because this is a third year courses, okay? We encourage students to retake, okay, if you don't do well, right? And we had, in the history, we had a failure rate more than 25% before in this class. I warn you and spend more time on this subject, right? And also make good use of our TA resource, right? So I don't know how many of you already fell into sleep, but I have to tell you how to prepare. The best way to prepare our final exam is to do assignment, every question, understand, okay? That won't be that straightforward, you just copy it, right? Okay, but you have nothing to copy because this is a closed book exam. Okay, that's all for today. So if you like to ask me a question, I will be here around.